Chris, CEO and co-founder of KETS Quantum, has been building prototype quantum communication systems and exploring their commercial potential for the last 18 years. After starting as a lecturer in quantum engineering at the Quantum Engineering Technology Labs, QETLabs, at the University of Bristol, where he helped to pioneer a next-gen chip-based approach to quantum encryption, he's now commercializing this approach in the quantum startup KETS Quantum. At KETS, we develop quantum-safe chip-based encryption to protect critical data from all advanced computer attacks. Chris holds a PhD from the Institute for Quantum Computing and a BASc Honours in Systems Design Engineering, both from the University of Waterloo. Quantum computing is advancing rapidly, and we'll be able to crack all the existing protections on our data and privacy. KETS develops quantum-safe chip-based encryption to protect critical data from all advanced computer attacks.
Thanks, Anna. I'm starting to feel old with that introduction. My name's Chris. I'm the CEO of KETS. Our claim to fame is that we have a chip-based approach to QKD hardware, quantum key distribution hardware. So really, I think in the 15 minutes, I'm going to try and tell you a little bit about KETS, but I'll really try and keep it to a bare minimum. Then I really like what Florian did from Quantique last week, dispelling some myths and signposting you to some practical resources and places. So I'm going to try and keep that up. That'll be the bulk of it. And then I at least work best by example. So we've done a few things in our past that kind of highlight some of those myths and signposting. So I'll show you a little bit about some of the things we've done, just so you have some things to hang your hat on and sort of maybe use cases you can use the technology in or that kind of thing, or what it looks like when it's installed. I'll try and keep an eye on the messages board, so do ask questions. I might save them to the end. I think I can still see everything I need to. So with that, really briefly, this is KETS. We're based in Bristol, UK. We have a couple subsidiaries in the EU. And again, we did the world's first demonstration of chip-based QKD, which we've now commercialized. And it's out there with a top 5 telco. It's out there in some of the Euro QCI projects. So very much solutions sort of exist. I'll come back to that point. Some people still think it's waiting to get here. And we just love our chips. So I'll show you a picture. I mean, this is what we're sort of not quite famous for, but this is what we're known for, I guess, is chips. This is what powers our devices. That's one of our beautiful little indium phosphide chips. It's about 2 millimeters by 6 millimeters, so about a quarter the size of your pinky fingernail. And it's got everything you need on there, a laser, 10 gig modulators to create qubits, basically, which is how you can exchange some quantum keys securely between different sites. And I mean, the analogy really is one of moving from sort of vacuum tube computing with other competitors that we have. They do it with fiber optics, to the transistor, and we do it with chips. You don't have to hook together an optical system by hand. It all just comes patterned on a chip that's tiny, that's nice and stable, that's ready to scale. It's given us a roadmap to bring costs down, because someone will know that the costs are a bit high because it's a new technology, but we've got a roadmap to bring them down. And then you get all sorts of stuff for free too. It's low swap by design, size, weight, and power, and that's mattered for some of our demos you'll see. But really, it just enables scalability. We can get sort of volumes up, costs down, and actually help this market take off. And then again, really briefly, in case you're interested in what we have in terms of products, we've got a QKD system. It looks like a server rack. You open it up, there's lots of air in there right now. We're going to keep shrinking it down, but for now, it looks like a server. And you can see some of our key rates at the typical distances that people quote on. We do BB84. There's plenty of protocols out there that you can use. And we'll come back and see some of the use cases we've used it in. And besides QKD, we also have a QRNG. It can be a standalone thing if you're interested in it. It can be a PCI card if you're interested in it. And it's around sort of 5 gigahertz in terms of entropy that you can get out of it. Because we made a choice that we didn't want to randomness expand the entropy to pick our keys in our QKD system. So we needed something that was very, very fast. That's it for the product plug. Sorry about that. These are the myths that I really wanted to get into, because they're out there unhelpfully pushed by some of the security agencies that are out there. And there's at least nuance to all of them. If not, the situation's just changed for a lot of them. So the first one, where's my cursor gone? Is you need specialized hardware and high cost. So maybe this is a bit more fair. But I mean, anything new costs a lot. Well, how much did your first iPod cost? I mean, it was extravagant, and now the costs are way, way down. you need to be able to start leveraging economies of scale, and people are starting to buy these things at higher and higher volumes. Um, and you've got all the vendors that know this. We're not dumb, that we need to bring down costs. And we certainly believe that chips is a huge way that's going to do that because it just makes the devices akin to assembling a modern PC where you plug a couple boards together and there you go in a day versus in the past when it took 6 months to sort of put these things together by hand. What else we got? Speed in the one-time pad. So in the security of QKD, if you want it to be sort of theoretically secure, you've got to use one bit of key for one bit of information. This is true. And lots of people knock it as being unpractical, but maybe for a video call like this or connecting with billions of people, it might be, but we're not going after the consumer market to start with. We're talking about those really high value enterprise applications, telecommunications backbones. If you think any sort of critical infrastructure when you're sending control signals, like in a nuclear power plant, I mean, those are small in terms of size, data size, control signals that are going along, open this valve, put this fuel rod in, that kind of thing, but also very critical that no one sort of hacks in there and alters that signal. So yes, if you want the full theoretic security, you got to use one-time pad, which means you're stuck at the speeds of the QKD devices, but there's plenty of high-value applications that are exactly here. It's just not for you and I shopping on Amazon, maybe, that we care about that at the moment. But you can use it with AES, the Advanced Encryption Standard. This is thought to be quantum safe, just like some of the post-quantum crypto algorithms that are out there. And the thing is, it's not a useless thing to start rekeying AES with QKD, because right now what's done is you use the current tools of the day, RSA, elliptic curves, and that's what we know quantum computers are good at cracking. And they also tend to sort of rekey them quite slowly, maybe once a day, once a week. And even if you move to post-quantum algorithms to rekey them, it's a conjectured security. And lots of them take a little bit more memory or time. So you're probably still going to be rekeying your AES system maybe once a day, once a week, versus a QKD device has pretty high rates. You can rekey sort of on the order of every second or even on the order of sort of milliseconds and things like that. So you're still going to improve your security, even though you won't be able to claim that it's information theoretic secure, if you rekey your AES systems with QKD links. Oops. Denial of service, this is a fun one. Yes, if you have just one single QKD link and you snip that fiber, you're going to deny a service. I mean, this happened in the 90s when we were just connecting to one bulletin board system. And what do? We built networks of these things. And so what's the solution for getting rid of denial of service for QKD is you build QKD networks. And these things are being built with redundancy in them. And the other bit is chips actually really help you there too, because chips are fabricated to be, I mean, they just are identical when they come off the fab line versus if you're sort of hand splicing something together with fiber optic modulators and components where you get some variation. Chips, they tend to be just identical, which means any one of our transmitters can talk to any one of our receivers. There's no sort of fingerprinting that goes on versus some of the fiber optic implementations are quite finely tuned and balanced. So you really do get one-to-one connections, but that's not the case for us. So chips help you with denial of service, and certainly networks of these devices help you with denial of service. And then authentication is another one that comes up because you do need for a QKD transmitter and receiver to start chatting securely. They need to authenticate themselves to each other. They need to know that Alice is talking to Bob and not Bobina or somebody else. And this is not something that magically quantum gets rid of. If you've never met the person in the past, then how do you know you're talking to who you are? So you can do one of two things. You can depreciate your keys. And again, sometimes I'd have you believe that this is astronomically cost prohibitive. And for certain cases, yes. But if you're a telecoms operator deploying equipment into your network, then that's a countable number of devices that all sort of get deployed from roughly the head office. It is easily conceivable to pre-share some key with your QKD device when it goes out into your network, and there you are secure. If you start going into larger situations where it really is sort of many to many on the internet, what you can do is use a post-quantum algorithm to do the very first authentication. And again, you might have some people scream at you that now you don't get the theoretic security. Fine, but we're practical people. Your customers will have assumptions they're willing to tolerate. And if you do this, then you still get an increased level of security because that post-quantum algorithm needs to be broken there and then as you do that first QKD session to break it and to break any future sessions. If it's not, then QKD is efficient in terms of generating keys. So you finish your first session and you save a little bit of key and you use it to authenticate the next time. And now the next time you're using a quantum key rather than just a post-quantum secured key. So you can still drastically improve your security, even if you authenticate with PQC means to bootstrap. I'm seeing some questions come up, but I think maybe I'm just going to save them to the end, but do keep chucking them in. A few more in there. People are talk about practical implementations and security proofs, and they talk about them slightly different to what we use classically, as if they're not standardized and stuff. I mean, it couldn't be further from the truth. We have 30, 40 plus years of academics working on security proofs for QKD systems. Now, the devil is always in how closely does that proof or that analysis match what you're actually installing in the real world. And this is no different from post-quantum algorithms and what NIST just went through to come up with their standards. And a lot of that was sort of examining how you had to build a post-quantum algorithm, and it's still expected you have to follow that recipe. So the same things happened with QKD devices. These things are well developed, but still a ways to go depending on how you're going to use them in the field. And let's just get out of the way right now. Some will claim that they have absolute or unconditional security. There's not a single method on the planet that enjoys this. If I sort of am talking on the phone to my mom and reveal my password, then I mean, I'm screwed no matter how good the underlying security of my phone is if somebody happens to be in that same cafe. So let's just forget the notion of absolute unconditional security. Anyone that's in the know that's buying these things, building systems with them, know that you write down your assumptions and figure out what you're willing to put up with and what you're not. And then there are standards in development. People again say that there's not standards for QKD devices. There's no security assurance. The community is well aware of this. There's been draft standards on the go for quite a long time in ETSI, ISO, a few other places. And now the other half of the parcel you're getting is security assurance. So you're getting people like the BSI in Germany. There's Nostradamus in the York QCI projects, and we've got something in the UK called QAssure that's looking at putting together a security assurance procedure that then a third-party test house can sort of run through, get one of our devices, and sort of run through this checklist of tests and make sure it does what it says on the tin and give a customer some confidence that what they're buying is now going to be secure. So all this stuff is coming online, but it's sometimes a bit chicken and the egg, because until networks are out there, until people are buying these boxes, then there's not a market for people to security assure them. But it's all starting to really kick off now. Almost done. Distance limits also always comes up. It's important to say that at metro scale networks, assuming you've got a decent fiber network, you can already get end-to-end security with QKD boxes and an optical switch in the middle. If you want to go longer, span a country, you can do trusted nodes. People will often sort of dig at this because you do have to trust these intermediate nodes. But we're doing that with our telecoms providers anyways, and most customers are completely fine with this. So maybe in principle argument you can have over cognac, sure, but in practice, this really doesn't matter. And in the medium future, you've got quantum repeaters and QKD satellites coming to really span the globe and remove that last assumption. I think that's it. Oh, last one. People knock it because I'm not going to put it on my phone tomorrow, and that's true, but that's not the market we're going after. We want to really secure the backbones of our comms services so that we can rely on them. And then you can think in the future about getting right down to the phone. And there's already instances of ID Quantique's got a QRNG in a cell phone with Samsung. So there's already instances of using quantum safe security to improve even things like mobile devices. Watch my time a little bit. I think I'm doing all right. So those are a lot of common myths. You're welcome to ask more about it, but they appear again and again. And they're really annoying because there's at least some nuance there, if not some downright, it's not quite accurate. And we really like NATO because they've got a very balanced approach when it comes to QKD versus some of the other ones say software's everything, and software's ultimately got to run on some hardware. Versus they're saying that it's a couple of improvements, which is roughly sort of what we've just been chatting about now, and many of them are coming online. And it'll be a key thing in securing our communications. And the last bit was practical security considerations. And I think these are just full stop, not even necessarily for defense. And they're kind of obvious, but I'll still state them. The first is, oops, and I've said it before, nothing's absolutely secure. So practically, when you're implementing these in a defense application or not, Write down your assumptions, work with some trusted people like some of the other speakers that are on this call that they can help you, or there's others out there that can help you write down your assumptions and know what your security actually is. Nothing's going to be absolute or unconditionally secure. Second one is there's lots of great vendors out there and solutions already exist. This is not something far off in the future. You can buy them from us. You can buy them from some of our friendly competitors, and you can really start building solutions right now. The third is it's a tool. It does not solve the world of cryptography. It does a few things really well. And 9 times out of 10, you're going to have to use other crypto tools as well to build a full solution. So this is going to be probably post-quantum algorithms as well. Key managers, hardware security modules to store keys, all sorts of stuff. And they all have to work together in a defense in depth, or the old passphrase was crypto agility kind of way. So know that when you get into this, you're not just buying a QKD box. You think about the application you want to solve, and then start picking your way like that in terms of all the pieces you need to bring, all the tools you need to bring to secure it. And so I should have had this picture come up now. The reveal is already there, but I mean, there are already tons of existing test beds. This is a picture from our friends at QBTech showing the North America, because one of these, I think, is a Canadian network. But there's plenty in North America, there's plenty in Europe and UK, and there's plenty in Asia. So you don't have to build everything from scratch. You don't have to buy 100 QKD devices and build your own network. There's plenty that welcome end users to come and trial new things. So you can get started quickly with a pretty low overhead. I think that's probably the best thing that if you're unaware of it, to look into in terms of signposting you. And then I mentioned it already, standards are actively being developed. I'll talk a little bit more about the one in the UK. So again, you're not waiting for 15 years to have a standard. These things are actively in development. There's draft ones from ETSI and ISO, and security assurance procedures are now already in draft form as well. And again, they'd love people to use them in real installations. So you can provide a real service by starting to play with these devices, use these standards, and feedback to them. Hopefully so good. So far so good. Last bit, I work from examples. So just to give you an idea of a few of the things that we've done playing with our devices, because it might help spur your creative juices when you're thinking about your own situation. We've used them to secure a downlink to a UAV with Airbus. We did this over daylight conditions, about 1 kilometer. So this was sort of a stepping stone to satellite QKD, which is going to help us get worldwide communications. But there's plenty of use cases you can think about there. There's sort of resources and exploration and things like that, or surveillance and things like that, where you want a secure downlink to get that data to the ground. That was a fun project. You can just sort of see the hint of a telescope at the back here. Sort of our device sat in this black box. I don't know whether you can see my cursor, and then came through a telescope link and went to the ground. I mentioned there's test beds out there. So one of the first was Paris QCI. This is building a quantum safe network in Paris. And it was sort of a precursor, actually, to the Euro QCI projects that plan to put an entire quantum safe network across Europe. And we were one of the vendors to come and help them start securing this. So just recently, we did one of these links. I think it was in the heart of Paris. I think it was one of the ones up here, and showed sort of what our devices could do in the lab, and then what happens when you actually put them on an installed link. I think it went to one of the universities and another location, and it worked quite well. So these kinds of projects are getting off the ground more and more. Oops. Oh, sorry, I meant to show you. Nice stable operation. Blue is our error rate, which is sort of what you monitor for security. And then black's the secret key that you're coming out. So you can see that you're nice and stable over the course of hours and stuff. Even on, so the top is a lab experiment. It didn't go that long. The bottom's over a real fiber. And you can see it works perfectly nice running under fibers under the ground in a city. I mentioned also that you're probably going to be putting pieces together. So we worked for a long time with BT. And something we had fun doing just last fall was we were bringing sort of a device for trial. They had a Juniper encryptor there, and we had a bit of extra time on our hands. So we said, why don't we try and use our device to rekey their encryptor and set up some quantum safe IPsec tunnels. So we did set up 2 of them and did a loop back over to one of their exchanges and back in their sort of testing site at Astral Park. And you can sort of see what we did. Over 17 hours, we were rekeying every 180 seconds, so much faster than they might have otherwise been doing in the field, and you were doing it with quantum safe keys. And again, you can sort of see the error rates in green here, roughly stable. I don't think we were working too hard on keeping it stable and had one of our prototype devices there. and some nice keys coming out in yellow. And you can read all about this. It went to OFC, and we talked about doing this kind of thing. The other bit that I mentioned was you're often putting tools together. So we partner with a post-quantum algorithms company because any of those algorithms need good randomness to bootstrap themselves. And so this is exactly what we did. We piped in our randomness from one of our quantum random number generators to their algorithm. And then they put that into a popular sort of open source crypto library. And really what we were doing at the end of the day was a quantum safe certificate. That was the application we wanted to do. And you needed to bring a couple of tools together in order to get it done. And this on steroids is we worked with some folks at Waterloo, really thinking about deploying a network of QKD devices, and not just QKD, quantum safe services, really. We brought post-quantum into this. And so this was largely a virtual network because we had limited budget, but we set up a virtual network in Waterloo, one in Bristol. A single one of those links was actually QKD devices. We simulated a QKD satellite and learned a lot of things about what it takes to keep this up and running, provision keys to people. And like I said, we also used post-quantum tools in there to keep the sort of underlying system safe. It was used within the system, but it was also, you could get quantum safe keys from post-quantum algorithms out of this key network, just the same you could get QKD keys out of the key network. And there's a whole website dedicated to it. We did about an hour and a half's webinar at the end, so you can really look into it and find out what that was like. And I mean, this was just two nodes coming together, intentionally messy, I guess, but it really did get complicated, which is kind of the point. When you're going to do a real solution, it is going to get complicated. That's why you need maybe some folks like that are on this call, get some help in terms of architecting your secure solution. Almost done. I mentioned security assurance. We did one with NPL focused on our QRNG. So basically a bunch of vendors gave them quantum random number generators to vet that they implemented the physical model that the vendor said. And at the end of the day, we're producing good entropy and good randomness securely. And there's a new one now. BT is leading it. Again, a couple of vendors and lots of universities there, really establishing a security assurance procedure. You've got standards for how the devices should operate and interoperate and interface with you. But you also want a security assurance procedure that a third party can sort of get a document, get a QKD device, and start running it through its paces. And if it follows all the security assurance, then at the end of the day, you should now have a third party that says, yep, this QKD device is secure, which is really crucial in terms of getting these things widespread and people buying them with confidence. I think this is my last slide. And then just get involved. This is one of our projects. We worked with something called the Quantum Data Center of the Future project in the UK, and we just looked at all sorts of use cases because it's a Pandora's box when you start looking at data centers and the need for quantum safe services. And that's really when we started layering on other tools to sort of our base tools. So we had an entropy as a service where you can distribute randomness with one QRNG, but to all of your servers in a data center, 10,000 endpoints. We looked at quantum secure links where you'd in the same box get a QKD device, an AES encryptor, and an add drop filter to put everything down the same fiber. So your classical encrypted traffic and your quantum keys. So it's just a really interesting project once you started looking at real use cases of how you put all the building blocks together to get full security at the end. But I think I've used more than enough time. And I think there's a couple of questions out there as well. So thanks very much for paying attention and the questions. I guess, do I just go through them and have a look?
If you want, I can read them for you, but I think it might be easier if you just read them and answer. I mean, I don't know. What do you prefer?
Yeah, I'm happy to read them. I'm going from the top. When we say we built networks to get around single points of connection failure, we managed to work out how to chunk up our comms into packets and then do packet switching. What's the analog for quantum networks? Okay, good question. Again, this is QKD things, QKD devices do quantum keys. You're not actually going to trust any of your data to it until you're sure that you've got a secure key. So this is a key network, all sorts of daisy chain devices. And you can combine keys if you're sort of going across a couple of links. It's just an XOR that happens at this trusted node. But basically, there's a key management system there responsible for knowing the topology of the network. And the user just walks up and says, I want to talk from A to C. And then it's the network that understands that, oh, well, I can go via here, or maybe there's a direct link, or maybe I got to go up to a satellite and another satellite and back down. But all that happens under the surface to establish keys. And I guess there is some analogies like packet switching. This is some of the stuff we did in that data center project. We call that sort of the quantum link 2 and 3 projects. We had a bit of software where our devices could sort of discover themselves like a classical networking device would. But it's a very similar analogy, and it's always keys you're establishing first, and you do that securely before you actually pass it up to a user. So the user doesn't have to care about any of this underlying stuff is, I guess, the key point. I hope I answered the question. If I didn't, put another one in. I'm believing your rack-mounted device, the first device for QKD, is for fiber communication and not free space. It can do either. We need a quantum channel that meets certain sort of technical requirements, but free space is perfectly fine. We've plugged them in to little telescopes on either end with fiber. You'll tend to get more loss that way, but it will work over free space because we work at 1550 and there's a transmission window in free space at 1550. But it tends to always get plugged into a fiber network, but it doesn't have to be. Many large enterprise organizations, such as the one I work for, are very cloud heavy. When and more importantly, how will QKD be cloud ready? Depends a little bit what you mean there, but I claim that it already is. What you need is your telecoms provider to invest in QKD devices and outfit their networks with it. Now you can get connectivity across sort of from your enterprise into a data center and back. Then you'll need depending on your security requirements, you might need a QKD device in your own basement as the enterprise, or maybe you trust your telecoms and that last mile you're willing to do as a post-quantum algorithm. It really comes down to your how paranoid you are. So you need the telco to sort of do your network, decide whether you're going to do a device in your own basement, and then you need the data centers to start outfitting themselves with them as well, so that you can get all the way in and all the way back out. The nice news is lots of telcos are doing exactly this. Lots of data centers are exploring this kind of thing. And the more sort of large enterprise organizations we have playing with this stuff, the quicker the market will come on and prices will come down. So nothing has to, it is cloud ready. Depends what you mean by ready. It has the potential to be cloud ready. There's some investment that needs to happen, but everyone can help sort of spur that on by getting involved in test beds and starting to sort of buy and play with these devices. But there's no I guess what I'm trying to say, there's no fundamental scientific breakthrough we need to make them cloud ready for data centers. In the BB84 QKD or similar protocol, we know that eavesdropping or interception during secret key generation can be detected, prompting both parties to discard the transaction and attempt a new one. However, what if a man in the middle prevents them from ever successfully generating a secret key? Wouldn't this result in a denial of service attack? And what fallback methods are available in such a situation, from switching back to existing encryption to other things? A couple of different things you can do. Again, this is why you build QKD networks, because they'll have to be sitting on a link or a series of links to do denial of service, and hopefully you have some redundant links that you can switch to. That's the solution number one you try. But it's also a reason why you'd like in your overall quantum safe system to have post-quantum methods in there and other things that you can fall back on. So it really depends on what your requirements are, but there's lots that you can do. There are much more in oops, sorry, I think someone was just commenting to somebody else. Someone was commenting to somebody else. What part of QKD device require it to be so big? Nothing fundamentally. There's lots of empty space in our devices because it's sort of our earlier devices. It's just electronic boards, looks like a motherboard of a computer. There's actually a processing motherboard in there too. I don't know where our picture went. There's a computer back here. There's a couple of PCB boards, and there's the chip in the middle. There's lots of empty space. And I guess what's stopping it is a bit more investment dollars, because like it's known engineering problems to shrink a PCB down to a little ASIC chip, to shrink the compute hardware, which in our case is a bit overkill to start with. So it's just a bit more engineering, but they're all known problems. It's stuff we've done before to shrink things into phones and things like that.
Maybe I can also add to this question from the hardware side. Most of the currently available devices use bulk optical components. And many of them, I mean, simply require basically all realizations of QKD require optical components because you are transmitting by using light, and you usually cannot, for some reasons that I'll mention later, you usually cannot use standard telco components, which are nicely integrated and compact and tailored now to large-scale applications. hence, you usually end up nowadays with these large boxes because you need, for example, optical modulators, SPAD detectors, or if you want to go to a single photon superconducting nanowire detectors, that's even bigger, and you end up with these large devices. But that's also related to the fact that this technology is quite young and now needs to go into these cycles of optimization. And one of the steps is actually moving to chips, to integrated photonics, and that's what Chris also mentioned in what his company is active in, and this will definitely improve the situation.
Thanks. Yep, agree with all that. The only other thing I disagree with is that last comment in there from MC who had to go, because I think he or she has misunderstood that it's QKD is a long way to go re-authentication. I hope I didn't get misunderstood. I mean, there is no secret for authentication that the quantum solves magically. If you've never met the person, then you don't know who you're talking to. So the only way of authenticating in a theoretic secure manner is you've met them and pre-shared a secret with them that you use the next time you're talking to them. So sorry, that's the only thing I point out, so no one gets the wrong end of that stick. Nothing needs to be developed for authentication. We got all the tools right now. But that's it, I think, unless I'm happy to turn over to the next speaker.